All right, welcome to Friday. Happy Friday. So today we're going to talk about radicals, square roots, cube roots, fourth roots. Okay, we get back into that, and then we're going to get into some rational fractions, exponents that are fractions. So that'll be pretty neat. So let's jump right in here. You can use this one if you want. So here's stuff that you should already know. So let's review some stuff here. 7 to the third power times 7 to the second power is the same as 7 to the fifth. Good. You add them, right? If you divide two powers of the same base, you can combine them by subtracting 11 to the second. If it's a power to a power, you multiply. If you want to simplify a square root, you try to find as big of a perfect square factor as you can. In this case, break it into root 25 times square root of 3, which is 5 root 3. Just like that, right there. If you want to rationalize and get rid of a root in the denominator, you multiply by root 7 over root 7, like that. That's called rationalizing. The numerator stuff, instead of multiplying to get 140, I'm going to break it down. I'm going to go root 5 times root 4 times root 7, like that. And so when we're done here with this one, I'm going to have root 7 times root 7 in the bottom makes 7, and then on the top, I have a 2 root 35. Just like that right there. So anyway, those are things that you should remember from before, hopefully. If you don't, there's a little refresher. Okay? So now what we're going to do is we're also going to, we're going to talk a lot about like cube roots, fourth roots, and we have variable expressions. So we got to remind ourselves what it looks like when we take square roots and cube roots of variables to a power. So the square root of x squared, what is that? That's just x. Good, that is a perfect square. Square root of x cubed, is x cubed a perfect square? Nope, it's not. So the way I like to think about this is what stuff in the radical is a perfect square, and then what stuff is left over. So in this case, I can pull an x to the second out, or x squared, and I can break x cubed up into the two factors x squared times x to the first. And then what happens with x squared is the square root of that becomes x, and then I'm left with a root x, so x root x. Okay, x to the 18th, is that a perfect square? By the way, they don't write the 2 on these, but there is a 2 there. I don't know, they don't write it just because that's it's the square, yeah, it's a square root. Okay, because now we can talk about, next page, you talk about cube roots, fourth roots. So the reason I wrote that in there is because hopefully you recognize, is x to the 18th a perfect square? Now 18 itself, the number, is not a perfect square, is it? But x to the 18th, or any variable to the 18th, is a perfect square. Because if you think about this, x to the 9th times x to the 9th is x to the 18th. So it is a perfect square. It is x to the 9th. And then how do you get 9 if you have 18 and 2? Divide. Yep. And so you end up dividing, and that's how it works. See, like right here, the first one, that was 2 over 2, right? Okay. This one over here is, well, it was 2 and 1, and so the 1 stuff was still in the radical. What about x to the 21st? Is that a perfect square? Nope. But part of it is. X to the, what's the biggest part, biggest factor of x to the 21st that's a perfect square? 20. Because you can break up the square root of x to the 21 into x to the 20 times x to the 1. So any multiple of 2, any power that's a multiple of 2 is a perfect square. So in this case, this is x to the 10th times the square root of x. Eh? Yeah? Yeah, what do you think there, Say? Okay, now we have multiple variables in here. So the way I like to do this is I like to break it up into 2 radicals. One of the radical is like the perfect root stuff. I factor it up. Perfect roots stuff or factors. And then this is like the leftover factor. The leftovers. Leftovers. You're making Homer hungry. What's a perfect root of x to the 20th? Is that whole thing a perfect square root? Okay, good. Ooh, make that into a 20. What about y to the 12th? Yep, because if this is square root and those are all multiples of 2, is z to the 3rd a multiple of 2? Nope, but the next smallest number that is squared, right? So the only thing left over here is a z to the 1st. If I multiply all those purple factors out, I get with what I started, right? So now over here I will have x to the 10th, y to the 6th, z to the 1st, and then left inside the root is z to the 1st. Huh? Okay. Why don't you try the next one? All right, so if you tried along at home, which you probably didn't, check your answer. There you go. Moving on. Now we talk about cube roots. So same concept, but now it's what times itself 3 times. So is the 8 a perfect cube? Yeah, because it's 2 times 2 times 2 equals 8. So 2 cubed is 8. So the cube root of 8 is 2. Cube root of 27 is 3. Perfect cube. Because 3 times 3 times 3 equals 27. Okay, now we get into some variables. X to the 6th. X squared. Why? Because x squared times x squared times x squared is x to the 6th. And how do you get x squared from 6 and 3? How do you get a 2 from 6 and 3? You divide 6 by 3 and you get 2. Or what times 3? Dividing is just multiplying backwards. What times 3 is 6? 2. Good. Now x to the 13th. Is that a perfect cube? Is 13 a multiple of 3? No, but part of it is, right? So x to the 12th, if you count down whatever your next multiple of 3 is, that's your where you stop, and then I have left here is the x to the 1. So this would be x to the 4 times the cube root. You got to put that 3 in there, that cube root of x. Yeah. The only one you don't have to put is the squared. You can leave it blank. Okay. What would happen if we had a 4th root? Well, it's the same concept. It's just what times itself 4 times. Gets you 256. I think this one is a 4. 4 times 4 times 4 times 4 gets me 256. And x squared times x squared times x squared times x squared gets me x to the 8th. So this is a perfect 4th root. It is 4x squared. Neat. Neato. Neato Frito. Okay. Next question. Any predictions for a 5th root? Huh? Any predictions? Yes. I think this is going to be 2. What do you think? 2 times 2 times 2 times 2 is, wow, 32. Good. And x to the 30th, is that a perfect fifth root? Yeah, x to the 6th, I believe. So if I take 2x to the 6th to the 5th power, am I going to get 32x to the 30th? If I take 2x to the 6th to the 5th power, am I going to get 32x to the 30th? There's no cough button on here. Yep, that would be, right? It's 2 to the 5th, and x to the 6th to the 5th is going to be x to the 30th. Good. So the answer to this one is 2x to the 6th. Perfect fifth root. All right, let's talk about some negativos here. So find all the real roots, all or 6 roots of 64. Geez, now we're getting into 6 roots. That could be 2 or -2, because a -2 to the positive 6 power is going to be 64, and a positive 2 is the same. You couldn't have the cube root of a negative, because a negative times a negative times a negative 3 times, or an odd number of times, does produce a negative. So this would be -6. But you can't have the square root or the fourth root of a negative, because it's an even number of multiplications, and that would never produce a negative. That's where, remember, we came into imaginary numbers. Remember? You remember that, right? Okay. So that's pretty hype. Fourth root of 81. 3 times 3 times 3 times 3. 9 times 9 is 81, and 3 times 3 is 9. So 3 times 3 times 3 times 3 is 81. That's a positive. Oh, you could have a negative too, couldn't you? Kind of like when we solve taking the square root of both sides, and we got to consider when we're solving the equation the positive and negative root, plus or minus. Kind of like that. You can't, no, you can't take like this, the fourth root of a negative. That's what I was saying. All right, let's keep trucking here. Now, now we got some cube roots. We got a mixed bag here. This is the last page, right? So we got a little mixed bag. So let's dice this up. 162. That's not a perfect cube, but part of it probably is. I bet you 8 is. 8 times 8 times what is 162? Or is it 27? 27 times 6, I bet. 120 and 42. Yep. 27 and 6. Okay, so we got our perfect cube part. We got our not perfect cube part. Our perfect cube part consists of 27, and then the non-perfect is 6. So 6 is not. So that multiplies to get 162. And then x to the 12th is a multiple of 3, so that whole thing is a perfect cube. So that cube root of 27x to the 12th turns into 3x to the 4th. And then I have the cube root of 6 left over. How to get what? The whole thing? Because I know that 27 is a perfect cube, it's 3 times 3 times 3. And I did write this over here just to kind of help a little bit, and then we can print off a table of powers for you, but I wrote perfect cubes over here, like up to so on. Perfect squares up there. They're usually pretty small, otherwise the numbers get huge. Like perfect fourth roots, 2 times 2 times 2 times 2 is 16. 3 times 3 times 3 times 3, 3 to the 4th is 81. They get big fast. 320, I'm looking for perfect cubes. So factors of 320 that are perfect cubes. So I can look over on my list there. Are there any factors of 320? 64. 64 and 5. Good. So now I factor that up into perfect cube, non-perfect cube. 64 is going to be part of my perfect cube part. 5 is my not perfect cube part. And then x to the 19th. 19 is not a multiple of 3, but the next lowest is 18 is. So that's x to the 18th and x to the 1 over there. So now this stuff here, the stuff I'm highlighting in yellow, that's a perfect cube. And I should have little 3's there. So cube root of 64 is 4, and the cube root of x to the 18th is x to the 6th. And then I can't do anything with the leftover stuff because it's too small to be a perfect cube. Fourth roots. What? Now there's a 7 out here. What the heck? There's a 7 out here. That's fine. Just leave it out there. It's just 7 times. Okay, so now I have 7 times whatever my perfect cube stuff is, and then my non-perfect cube stuff. Perfect cube, or not cube, fourth root, sorry. Fourth root of 625. That's going to be 5. I'm pretty sure. 5 times 5 is 25. And if I square 25, I get 625. So that's 5 times 5 times 5 times 5. So the whole 625 is a perfect cube, or fourth root, blah, blah, blah. And then x to the 8th is my next smallest number that's a multiple of 4, right? You can also kind of think of it as like, how many 4s go into 10? 2, with 2 left over. So the leftover stuff is always the stuff in the radical still. Radical, dude. So now what do I have left here? I have a 7 times a 5x to the 2nd, and then I'm left with the fourth root of x squared. So 7 times 5 times x squared, that's 35 x squared times the fourth root of x squared. Look at that little puzzle. Something you'll never have to do in your life. We're developing your abstract thinking abilities here. This is the 21st century. We're not just hunters and gatherers anymore. I wish. Sometimes I am. If I go up to like the boundary waters and I live off the land for a while. Catch fish and eat them. All right, let's wrap this up here before we all fall asleep. What's this x to the 11th doing out here? Nothing, it's just out there. It's just multiplied by, just leave it out there. So x to the 11th times, what's my perfect fourth root stuff? What's my not perfect fourth root stuff? My perfect fourth root of 128, that's going to be, let's see here, 4 times 4 times 4. No, 2 times 2 to the 4th is 8. So does 128 divide by 8? I feel like I should have like a pause button, like after these messages, we'll be right back. All right, so I'll pause it. Okay, we figured it out, 16 and 8, and then x to the 24th, that whole thing is actually a perfect fourth root. So we have x to the 11th times 2x to the 6th times the fourth root of 8. Clean that up, write it all as one thing. That's going to be 2x to the 17th times the fourth root of 8. It's not the square root. It's the fourth root. So nothing times itself 4 times is 8. 2 times 2 times 2 times 2 is 16. All right, last one has a fraction out here, 2/3, so that's really scary. So we have 2/3 right there times, now we got perfect fifth root stuff and not perfect fifth root stuff. So perfect fifth root is 729. Oh, crime in Italy. Let's see, we have, no, it's not going to end in a 5. I think it's going to be a 3, right? Wasn't it a 3? 243 and 3? Yeah, that's what it was. 243 and 3. 243 is a perfect fifth root. It's 3 times 3 times 3 times 3 times 3. And then x to the 25th is a perfect fifth root, and x to the 1st is not. So now, and maybe some of you are like, what the heck? 3 times 3 times 3 times 3 is equal to 243. That's why we broke it up into 243 and 3. And so now we have 2/3 times 3 times x to the 5th times the 5th root of 3x, which can be finally written as 2/3 times 3. Those cancel out. That's 2x to the 5th, 5th root of 3x. Holy cow, we made it. I made it through the day. All right, that's it for today. Hopefully the video helps. Ciao, have a good weekend.